Something happened. Is it recording? Okay, I hope it's recording. All right, well, good morning and happy Monday. We will continue on kind of working through neural networks, and the idea here is to illustrate an application of gradient descent, and so what we've established so far is the structure of a neural network, how forward feed works, how we go from our input values of x to our predicted value of y hat. Okay, and now we are working on figuring out the gradient. Okay, which is basically that process of figuring out the gradient is back propagation, and we want to know how y hat changes when we make changes to our weights in our W2 matrix and our weights in our W1 matrix, because this is when we do gradient descent, what we are trying to do is we are trying to find the optimal values of W2 and W1 in those matrices. And so we want to find the values of W2 and W1 that produce a minimum, or at least a local minimum, for our loss function. Our loss function measures the difference between our predicted values y hat and the actual values, and we want to find the values of W that minimize that distance. And so in order to apply gradient descent, we need to calculate the gradient, which will tell us which direction is uphill. And then once we find that, we take a step backwards and we work our way downhill. And this is, we take this iterative approach to arrive at a local minimum. And the reason why we do this is because even if we find the gradient, trying to just solve for the gradient, setting, the gradient equal to 0 and solving, that would be quite challenging. So we don't try to set it equal to 0 and solve in an analytic manner. Rather, we kind of get an approximate answer, or at least hope to converge to some kind of solution by using gradient descent. And so this is kind of where we have left off. We said our loss function measures the difference between each value y and its predicted value y hat. This is in the summation form. We also have a form in matrix notation, basically y minus y hat transpose times y minus y hat, the matrices y minus y hat. And that does the same thing because you're multiplying all the values together and adding them up. And we have these two gradients to compute. An important kind of guiding principle is that because in gradient descent, we are going to be adding the gradient to the estimated values, to our kind of current values of the W1 matrix and our W2 matrix, because we're adding the gradient to those things, they need to be the same dimensions. So the W1 matrix is 2 by 3, so our gradient also needs to be 2 by 3. Our W2 matrix is 3 by 1, so our gradient also needs to be 3 by 1. And on Friday, we went through the process of finding the gradient with respect to W2. We also kind of went through the process of finding the gradient with respect to W1, but we kind of had to cut. We didn't completely finish everything, so we'll finish that process out here. Okay, and again, this is to kind of illustrate the process. In a production setting, if you were to do any kind of neural network, or whether it be a convolutional neural network or a large language model or things like that, you would not be finding the gradient in this kind of by hand manner, right? And you wouldn't be doing gradient descent in the manner that we will be doing in this class. But this is kind of a very manual, to kind of illustrate all of the little pieces. I don't know. It's kind of like building your own little science experiment at home, where you're like, using, I don't know, making an oven with tinfoil and magnifying glasses or mirrors or something like that, to kind of just illustrate some of these things to learn and understand. And we will get a working neural network that works using just kind of all of these operations that we're doing. And hopefully that sheds some light on how this works. But of course, in the real world, when people actually do neural networks, we have these very kind of efficient computer algorithms that basically do this kind of thing, but they do back propagation, with a network graph. Okay, but okay, so we have we've successfully calculated the gradient of the loss function with respect to our second weight matrix, and that is in the form, it's 3 by 1, and we want to find the gradient of the loss function with respect to our first weight matrix. And so we went through this process, and so we covered all of this on Friday. Again, the way we're working out on this is we're kind of just focusing on one value at a time right now, the nth value in y and our nth prediction, and then as we work, we'll eventually try to expand it from just the nth observation or the nth value to the entire matrix of values. But when we do that, we also run into kind of some dimension issues, and so we kind of have to keep track of all of the dimensions. And so I'm writing the dimensions underneath here. Also, a reminder that what we are doing is not strictly in linear algebra. We borrow the notation from linear algebra because we are multiplying matrices together, and linear algebra provides a nice notation that we're familiar with, that we can understand. But also at the same time, we're doing things like element-wise matrix multiplication, which is not a strictly linear algebra operation. Okay, so we'll kind of plug in our results so far here, where we have, as we're calculating the gradient of our loss function with respect to our first weight matrix, we're basically taking the difference between our actual value and our predicted value, and we're multiplying it by f prime of the value zn, the nth value of z3, which basically is the value before it gets transformed by the activation function into our y hat value. We're taking our second weight matrix and we're transposing that, and this is a 1 by 3. And then we want to know, okay, well, how does A2 change with respect to Zn2? So A2, the nth observation in A2, how does that change with respect to the nth observation in Z2? Well, that's, the nth, I guess I should say the nth row in A2 consists of applying the activation function to the nth row in Z2. So we can just say, all right, well, we'll take the derivative of this. Now it's a little bit kind of, it feels a little tiny bit wonky because there are 3 values here, okay? And so the gradient of the loss function with respect to W1, the result should be a 2 by 3, okay? Because W1 has dimensions 2 by 3. And so, as we kind of work through this A matrix, it's n by 3, and we are just looking at the nth row, but there's still 3 values there, okay? But you could, if I wanted to, I could further break this out and just say, okay, well, we're going to just look at the first value in the nth row, and then we'll look at just the second value in the nth row, and we'll just look at the third value in the nth row. And if you were to do something like that, okay, you'll find it's going to be kind of the first value in our W2 matrix multiplied by kind of the first value here. And so eventually we will have, just kind of jumping ahead here, we will have this element-wise multiplication between the elements in our W2 matrix and the elements in the nth row of our Z matrix. Okay, so it's the first element of W2 and our first element in the nth row of Z2, our second element of W2 times our second element here. Okay, but I just kind of leave it off here. And then we want to know, okay, how does that nth row in Z change with respect to our first weight matrix? The nth row in Z is 1 by 3, and it is the result of multiplying our X, our nth row in X, by our weight matrix W1. Okay, and our weight matrix W1 is a 2 by 3. The nth row in X is 2 observations. And so we're multiplying this 1 by 2 by a 2 by 3. And again, it feels a little bit strange taking the gradient or the derivative of a 1 by 3 with respect to a 2 by 3 matrix. But if you kind of think about how all of these elements are being multiplied together, okay, and we say, all right, well, our 3 values in the nth row of Z look kind of like this, okay? Basically, we're taking the first element of X, our nth row of X, and multiplying it by, an element in the first row of W, okay, and we're taking the second element of X, our nth row in X, and multiplying it by an element in our second row of W. And we could see that changes to anything in the top row would result in a change of Xn, and any change in our second row, okay, would result in a change of, basically multiplied by Xn2. Okay? And so, with that in mind, we can say the derivative of our nth row in Z with respect to W1 will end up being a 2 by 1 matrix, which will be the transpose of this. And so we'll put that in here. Okay. Now again, the dimensions of this all feel a little bit, if we go directly into this, the dimensions don't line up. So, we could break this down further again and just say, okay, what is the gradient of J with respect to W1? And we could derive each of these terms individually, okay? And, I could expand all of my slides. So I have, 6 separate slides for all of these things. I avoid that, and if we wanted to, we could. But basically, you would take they align in the way you would expect. You take the first element of Xn for any values in the first row, or you take the second element of Xn for anything in the second row, because at the end we want our gradient with respect to W1 to be 2 by 3, and so. If we rearrange these terms and we do this and we get, a 2 by 1, and we have element-wise multiplication here with a 1 by 3, the result here is going to be 2 by 3. Okay? And again, in linear algebra, this kind of stuff of just taking terms and rearranging them is not allowed. Okay? This is not a thing we do in linear algebra. And I cringe a tiny bit, like, I guess one of my fears is that another professor is going to look at my lecture slides and be like, "What are you doing here? This is this is illegal." But again, we're not doing strictly linear algebra. We're borrowing the notation from linear algebra because the notation of multiplying matrices together is easy to understand and provides a nice way to kind of do a whole bunch of these terms all at once. Okay, because effectively what we would have to do is we would need to do each of these terms individually. Okay, there's these six of these terms, and we would have to we would have to do each of these terms individually. And if you do that, you'll see that all of these elements do line up in the way that is kind of conveniently arranged here. Okay, and so so anyway, this is what we have. This is just for the nth observation. Okay, and then so we can kind of try to expand from just the nth row in X to the full matrix of X, and just the nth observation of Y to kind of our full column of Y, and so on and so forth. And if we do that, the dimensions still align. We do have to kind of switch from just scalar multiplication to element-wise multiplication between our column of Y values and our column of Z values, but it still works out, and the result still will end up being a 2 by 3. And so, expanding from just the nth row in X to the full X matrix, we have a 2 by n. Okay, this whole thing is n by 1 times n by 1. This combines into an n by 1, and this is multiplied by 1 by 3, so this will combine into an n by 3. And over here, this when we expand from the nth row in Z, which is a 1 by 3, that becomes n by 3. And so this whole thing multiplies. We have an n by 3 multiplied by an n by 3 element-wise multiplication. So this thing multiplies out to be n by 3 as well. And so now if I multiply X by all of this, which is n by 3, we will get a 2 by 3 matrix. Okay, and so this whole thing we'll call delta 2, and this is our result. So this is our gradient of the loss function with respect to our first wave matrix. Okay, and this is the proper dimensions of being 2 by 3. All right, and now we will turn all of this into code. So let me, before we do that, let me give you your first view quiz answer. Oh, where is it? Okay. Okay, first view quiz answer is A. A as in apple. A as in apple. All right. So here we will just take our function. I'm going to just create a function called sigmoid, and this is our activation function, and this will just take any value that we plug in to it, and it will return the sigmoid of the thing. Okay, so this is very straightforward, I think. All right. Our training data, kind of our original data, I just had these 3 observations, 3 by 5, 3 hours of sleep and 5 hours of study, 5 hours sleep, 1 hour study, or something like that. And these were my exam scores, 75, 82, 93. Now, in order for our thing to work, because our output, remember the result is we're activating our final predictions. Y hat is the result of passing Z through our activation function. Our thing is only able to predict values between 0 and 1. Okay, so what I'm going to do is I'm going to just divide everything by 100. Okay, and so that will give me 0.75, 0.982, and 0.93 for my values of Y. I could have chosen any other kind of scaling thing, but here just dividing by 100 is simple enough. All right. Also, with the X, technically I could plug in values as large as 10 and any value from negative infinity to positive infinity, but again that sigmoid activation function is most active, or has an appreciable slope between, say, -3 and +3, or -4 and +4. And once you start getting past x equal to 5, you're asymptotically approaching 1, or if you go past -4, you're asymptotically approaching 0, and you have very, very, very little slope. Okay, it's very, very, very flat, and so you often get stuck in these kind of flat-ish regions. And so one strategy is to kind of divide by the column max, and that basically turns everything to be a value between 0 and 1. It's not necessary to necessarily have it between 0 and 1, but just this is kind of a simple operation. So our first set of values will be what? 0.3, 0.5, and 1. And then here I'm dividing everything by 5, so we'll have like 1, 0.2, and 0.4 for our second column. Okay. Here I just have flexible names, okay? Just so that later on, if I wanted to change it from having 3 nodes in the hidden layer, I could just change it from 3 to 15 or whatever number I want to say. Okay, so I have input layer size, output layer size, hidden layer size. Okay, so to do forward feed, our mathematical notation is we're doing our input matrix X times our first weight matrix W1, and so on and so forth. And so I'm going to set up my first weight matrix. Now, arbitrarily, I'm going to just fill it in with the number 1. Right now, it doesn't really matter. Probably later on, I'm going to have random starting values, but just to kind of get the structure of our things, I'm going to just create my first weight matrix, W1, which will be 2 by 3. Input layer size is 2, hidden layer size is 3. And then my second weight matrix is 3 by 1. So number of rows is hidden layer size, number of columns, output layer size, okay? And then so the forward feed is X times W1. That's right here, and this is going to give me Z2. Then I apply the activation function to Z2. So I'm just doing this operation. F of Z2 gives me A2, so I call that A2 right here. Then I'm going to take that output, A2, and multiply it by W2, our second weight matrix. A2 multiplied by our second weight matrix. And that will give me Z3. And then I apply sigmoid to Z3 to get my y hat values. Okay. So all I'm doing is I'm just going directly from the mathematical form into kind of code form here. Okay. And I guess sometimes when you see a bunch of stuff mathematically and then it says, oh, let's just code it up, it feels like that leap or that transition feels kind of overwhelming. And I'm hoping that these slides just show like, yeah, if I said turn this into a function, this is probably what you would write, exactly what you write, right? And then if I said, all right, let's do forward feed here, or let's turn this into operations, and you look at this, you go, oh yeah, all of these operations make sense. There's no shocks here, okay? All right, our cost function, this is the loss function that we want to minimize. We are going to take the difference between our actual value y and our predicted values y hat, and I'm just going to do y minus y hat. We'll square that difference, and then we'll sum them up, okay? And then here I have this constant being multiplied, this 0.5, just so it matches the equation, but this is unnecessary, but it's in there, okay? And so right now I just say, hey, what's the difference? What's the sum of squared errors? And right now it's 0.0153, which doesn't mean a whole lot to us right now, but this is just kind of our current value. Okay. We want to we'll need a function for the derivative of the activation function, which comes directly from our notes last week as well. So I think so if I said what's the derivative of the sigmoid function, so this right here is just following quotient rule, we have e to the negative z, 1 plus e to the negative z quantity squared, and that's all I've written here, e to the negative z, 1 plus e to the negative z quantity squared. Okay, so it's just turning this into this what we have here. Okay. All right. And then this was the result. We went through that whole process of getting our gradient with respect to W2, and this is what we found. We said it's going to be A2 transpose minus y hat element-wise multiplication with Z3. And so we'll call this part delta 3, which is going to be y hat element-wise multiplication, just the star of sigmoid prime applied to Z3, right? And that whole thing is negative, okay? Or like we put the negative sign in front of that. And then here we just have A2 transpose. So that's what I have, A2 transpose times delta 3, okay? So again, if I said turn this into some code, you might write something exactly like this. All right, and then same thing over here for our gradient with respect to W1, right? I have, X transpose, and this was the work that we arrived at earlier, delta 3 times W2 transpose element-wise multiplied by F prime of Z2. So we'll call this thing delta 2. This is the equivalent of having delta 3 times W2 transpose element-wise multiplied by sigma prime of Z2. And so if I have that, then our gradient with respect to W1 is going to be X transpose times delta 2. Okay, and that's that. So let me have this opened up over here. Let me close all of this out. So we'll run all of this code. I've just transformed my X into just values between 0 and 1. I've transformed my Y's to just be scaled between 0 and 1 as well. Okay. Input layer size, output hidden layer. This is all of this. Okay, W1 is just, right now it's just all ones, and it's a 2 by 3 matrix. Okay, and then I could forward feed Z2 is going to be n by 3, and then we apply sigmoid function. A2 is also n by 3. We can see it's 3 by 3 forward feed. So our W2 matrix is 3 by 1. Okay, right now it just has ones inside of it. And if I do A2 times W2, then Z3 is going to be 3 by 1, and then I can apply y hat. Okay, so right now my y hats are terrible compared to my y. So my y's are, my y's are 0.75, 0.82, and 0.93, and I just have 0.91. These are just arbitrary values starting off with 111. Okay, and then so my cost, the cost between y and y hat is currently this. Okay, my gradients, okay, and we can skip that, are this, and so I can kind of just check, and I just want to check the dimensions. The gradient with respect to W2 should be 3 by 1, okay, and the gradient with respect to W1 should be 2 by 3, okay, and that is the case, so that's a good sign. And what we want to do is, if we do gradient descent, so once we have our gradients calculated, what we want to do is we're going to apply gradient descent, which is going to take our current value minus some scalar times our gradient. Okay, and so this scalar was arbitrarily chosen, just a little bit of trial and error. Usually the recommendation is you start off with a small scalar, and then you just try to keep making them bigger until things start not working, and then you go back to a sufficiently small one where it still works. Okay, so again, gradient descent, you just kind of take your current values. Right now, my current values of W1 are just all ones, okay? And wait, so let's see. Here are my current y hat values. And so I'm going to do take my current values of W1, subtract off the scalar times our gradient. I'm going to take my current values of W2 and subtract off the scalar times our gradient with respect to that. Right now, my current cost is this, 0.0153. And then but I've updated, now that I've done W1 minus the scalar times dj dW1, my W1s are no longer all ones. They have been modified ever so slightly, okay? And the hope is that we have taken a step in the correct direction, that we are taking a step downhill. So we'll just kind of check this, okay? And so I'm going to do forward feed again. I'm going to just say, all right, now that I have a new set of values for W1 and W2, W2 is no longer all ones. Now they're 0.93. We'll see, does this give me better estimates, okay? So I do forward feed. I do x times W1. I do sigmoid of Z2, I do A2 times W2, and then so now my new y hats are these, okay? So my old y hats were this, 0.91, 0.88, and 0.917, and my new y hats are 0.899, 0.865, and 0.903. And we can ask, is this any better? So we'll calculate cost 2, and we'll compare. Cost 1 was 0.015, and cost 2 indeed is now a little bit lower, 0.012. So, you know, it's hard to tell. You know, are these that much better than these ones? I guess. But yeah, when we use our loss function to measure, we can say, yeah, our cost indeed has gone down, which means we have taken a step in the correct direction. And we're going to just basically repeat this process, all right? We just run a loop where we just say, all right, let's do this again and again and again, and we'll keep taking steps downhill. I'm going to skip over this numeric gradient checking for now, but then I'll come back to it, okay? So I'm going to run a loop where I just do the gradient descent. And this time, rather than just starting off with all ones, I'm going to just start off with random values in my W1 matrix and my W2 matrix. And this is, again, when you do gradient descent, there's no guarantee you're going to find the minimum. And so a lot of times we say, you know, just pick some random values and then allow gradient descent to run. And then when it kind of stops running, you know, see where you are. And then try running it again, but this time with different random values. And you'll start off at a different location, let it run downhill, and perhaps it meets, you know, ends up at another successful place, or maybe it ends up somewhere else. Maybe it also gets stuck. So here I'm going to just start off with some random values. I'm going to just set a seed. I'm going to pick 6 random values to go into W1, 6 random values to go into W2. I'm going to keep track of my cost values, and I'm going to run 10,000 iterations, okay? And within each iteration, what am I going to do? I'm going to take my current values of W1 and W2 and use them to calculate my, my predicted values y hat, okay? And I need those y hats to calculate what my gradients are. And so these are just the formulas for the gradients. You know, y minus y hat times sigmoid prime for delta 3 and all of this. So this is the gradient with respect to W2 and the gradient with respect to W1. So I do forward feed to get my y hats. I use my y hats to calculate my gradients. And once I have my gradients, dj dW2 and dj dW1, I use that to do gradient descent, which is just take my current value of W1, subtract off a scalar times the gradient, take my current value of W2, subtract off a scalar times the gradient, okay? And I just repeat this over and over and over again. Every time I get a new set of W1 and W2 values, I run forward feed again to get a new set of y hats. Once I get my y hats, I recalculate my gradients. Once I calculate my gradients, I update W1 and W2 and repeat, okay? New W1, W2, new estimates for y hats. Okay, so I run this and it is done. Okay, and I can say, all right, well, what is W1? Okay, this is the resulting set of weights in my first weight matrix. they mean absolutely nothing to me. I have no idea. Okay, this is my weights for my second weight matrix. But I could see, all right, well, how close are my predicted values? Okay, my predicted values of y hat are 0.749998, 0.8200, and 0.92984, which seems pretty good considering that the actual values are 0.75, 0.82, and 0.93. So it seems like we have succeeded. Our cost is on the order of 10 to the minus 9. I could plot how our cost has changed, okay? And so we could see we started off with bad cost, and in the beginning our gradient immediately took us downhill. We kind of got stuck in a flat-ish region, and then we found a location somewhere along the way where we were able to improve our cost, and then now we're not able, now we're kind of stuck again. And well, we probably found close enough. We're probably not going to improve our cost any more dramatically than this. Okay. You can also plot the log of this, and so basically improvement, kind of flat, and then now we're just, anytime you see a diagonal line in a log plot, it just means you're improving by a multiplicative factor. So basically, like if you shrink it by, if the error shrinks by, 1/2, and then the next it's a quarter, and then 1/8, and a 16th, and so on and so forth, it would look like a diagonal line in the log plot. Is you're just kind of, by a multiplicative factor, you are improving. Okay. So that was kind of doing kind of manual gradient descent, and I hope this code kind of makes sense there. Let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Okay. All right. This here, which I kind of skipped over, but I'm now revisiting, this is called numeric gradient checking. So one of the big challenges with, any kind of machine learning stuff, or just, computational statistics and math in general, is there's always kind of this thing of like, my code didn't return any errors, but I don't know if I did the mathematics correctly, okay? Where you feel like, okay, well, I didn't run into errors, so that's correct, but I'm multiplying these numbers, and I'm not sure if I'm multiplying the correct numbers together, and so I'm not even sure if these results are correct, right? And that's kind of this fear that we often have, or at least that's a fear I often have. And so we do have a way to kind of verify our answers a little bit, okay? And one of this is numeric gradient checking. So we have calculated, we did the derivation, and we got our gradient, and we said, okay, the way we're going to calculate our gradient with respect to W2 is going to be y minus y hat sigmoid prime z3 for delta 3, and then we do A2 transpose times that. And then the way we're going to get our gradient with respect to W1 is we do this, and we do this. And we're just hoping, well, not hoping, but we went through the derivation, and I said it's correct. So, you feel confident. But, if you did this yourself, you might be like, well, this is what I got, but I'm not quite sure if this is right, okay? And so we can kind of do a little bit of like manual legwork, and we can just say like, okay, if I calculate the derivative of x squared, like analytically I get 2x. But you want to just say like, okay, is that actually the derivative? Well, one way you can kind of verify is just mathematically or numerically, you say, let's look at the number 5. When I plug in x squared is 5, it's 25. And then I could add, using the definition of the derivative, it's basically as, f of x plus h, minus f of x divided by h as h goes to 0. And so we could just try adding a tiny little h and seeing if computational components. So if I do like 5.01 squared, what do I get? And am I going to get a value close to 10? And we do. And that's basically what we're going to do here. So I'm going to just say, all right, let's say we had our matrix of all just ones in W1 and W2, and I can calculate my my y hats and my current cost, and my current cost is this number 0.0153, and I can get my gradients, and here I want to estimate my gradient numerically. And so what I'm going to do is I'm going to try adding a tiny little value, like 10 to the minus 4. Okay, I'm going to add 10 to the minus 4, and I'm going to try adding it to each element in my W1 matrix. So in my W1 matrix, I have 6 elements. And so when you calculate your gradient numerically, okay, or estimate your gradient numerically, you have to go element-wise. Okay, you're not going to add 0.0001 to all 6 elements at the same time. You just do it to the first element, okay? Because remember, it's like a whole bunch of partial derivatives. So we just want to say, all right, if everything else stays the same, if elements 2, 3, 4, 5, and 6 stay the same, and I'm only going to just change the element in the top left corner, I'm going to just add a tiny 0.001 to it. How does that affect my y hat? And then how does that affect my cost function? And that's basically what we're going to do here. Is I'm going to say, all right, here is my W1 and W2 matrix. They're all just right now just all ones, which is exactly what we started off with. And then I'm going to just add 0.0001 to just my first element. So first I'm going to just do it to the first element. And now that I've done that, I'm going to go through forward feed and say, all right, what are my new y hat values? And then how has my cost changed with respect to that? So I can just say, all right, let me just set I equal to 1 here. And I'm going to just say, all right, let's go through this. And then so my W1 matrix is basically all ones, except this one I've added a 0.001 to it, okay? And then I'm going to say, all right, let's do forward feed. Okay, so currently my y hat values are this, and then I'm going to just do forward feed, and I'm going to just say, okay, how have my y hat values changed? And they've changed ever so slightly, okay? And I can say, all right, what is my cost here? Okay, my cost here is this, and that looks almost exactly the same as whatever I used to have. My current cost was this, okay? Okay, and so it has changed ever so slightly, okay? There's just the slightest amount of change, and so we want to know, okay, how has the cost changed versus the current cost? And then we're going to divide by the size of E, okay? And so this is going to go into kind of, my first element here. And then so as far as my numeric gradient goes, I'm going to punch in this, put in that thing, and this is going to be my estimate here, okay? And then I'll do this for all 6 elements. So that's what this this loop does, okay? And I basically do the same thing for my second weight matrix, the gradient there, okay? And then and now I want to compare how does the analytic gradient that I got by doing kind of my analytic calculation of y minus y hat, sigmoid prime, all of that. This is my analytic gradient. How does that compare to the numeric gradient where I kind of just went element by element and I just added a 0.0001 and saw, what effect did it have on my predictions and thus my cost. And the hope is that these two things will look similar, okay? So the analytic gradient said, okay, the gradient, your partial derivative in that top left corner was 0.001210.512, and then when we did a numeric estimate of it, we got 0.001210.406. Okay, so a tiny bit off, but pretty close to each other that, we feel comfortable with this. Okay, so again, the numeric gradient, these are estimates by basically adding a tiny little 0.0001 to it to kind of manually estimate or numerically estimate basically your derivative or your partial derivative at that point. Okay, and so this is kind of a way to kind of just check, like, did I do my math correctly? And that's what we have. And this is just to kind of get like a percentage difference. And so this is on the order of 10 to the minus 5 for a percentage difference. This, for the second weight matrix, are percentage differences on the order of 10 to the minus 6. Okay, so that is numeric gradient checking. And it's, this kind of numeric check is handy, especially when you start doing math and you end up in a territory that you're less familiar with, and you can just, you want to just verify, like, did I do this correctly, right? And it's always comforting when, your results match, other results that you got from a different method. So, okay, so this is, so that's that. We'll wrap things up here. So Wednesday you have your midterm exam, and then Friday we'll just revisit neural networks, and we'll do it, apply it to like the most very basic, like handwritten digits data set, which is kind of a fun application, I think. All right, so we'll wrap things up here. Have a great rest of your day, and good luck as you study, and we'll see you Wednesday. Oh, I need to give you the third answer? Okay, third answer is E. E as in elephant. E as in elephant. Okay. Now you guys can go.